Good afternoon, everybody. It's great to see this large and diverse audience. This is our first uh, workforce development seminar series for this academic year and for this semester. Welcome. You will have a distinct pleasure to enjoy a presentation from our distinguished leader, Dr. Peter Elkin, who is a professor and chair of the Department of Biomedical Informatics. And he will introduce the series of biomedical informatics. But before he starts, I want to give you a broad overview of what the CTSI-sponsored Workforce Development Seminar Series looks like, and if you're interested, where you can find additional opportunities. So I'm guessing you probably learn about this workshop from the emails that you all receive. And in case you don't check your emails frequently or you can't find the right email, we have a website where all courses are posted for the semester and for the year. And you can find the schedule. You can find different workshops that may not be offered this year. And you can find workshops, specific workshops that's been recorded and open to people a year around if they missed them and wanted to see them at another time. So this is our current menu of the workshops that we have that you will find on the website. There are a variety of topics related to conducting translational science, working with patients, working with data that you're mostly going to be hearing today, collecting data, challenges with designing studies, various strategies for designing studies, effective strategies for teaching. There's a wealth of information that you can receive by attending those workshops. Most of them are remote, but some of them are in the classroom face-to-face from the university experts. So please take advantage of these opportunities. And we try to schedule them so no seminar series overlap too much, so you can take as many of the workshops in the semester as you can. Specifically for the series that starts today, this is the first year that we are trying this hybrid format. So Dr. Elkin will present to you today an overview of biomedical informatics and other workshop series that's available in an extensive library of courses and workshops that he and his team have created. So anybody who can sign up and on the call today and will attend today's presentation will have access to the library and can peruse and pick and choose and complete workshops at their own time. We just wanted to summarize that very often people ask questions because this is not a full-time course. This is about 90-minute presentation and other workshops are about an hour long. And if you're not finding information that you need, but maybe related to your study or to your expertise, look in the other workshop series. There is a lot of information related to data science and using data that's presented in other workshops that's summarized here. Also, and that applies to all workshop series, if you complete all workshops of the series, or as many as the instructor will state, so for this one, it's all workshops, you will receive a certificate of completion. Liz and Catherine keep track of your attendance because we are on Zoom, so we know when you're there and when you're not there and when you leave. And automatically at the end of the semester, if you completed all the workshops, you will receive a certificate of completion. In addition, Biomedical Informatics is about to offer an advanced micro-credentials that has required courses in addition to this workshop. You can take additional courses offered by Department of Biomedical Informatics, listed here, and select from elective courses that's also offered in the biomedical informatics. And that will give you advanced micro-credentials. And Dr. Elkin can tell you more about that. And those of you who are eligible for CME credit will also receive 1.5 CME credit for today and up to 8.5 CME credits for the entire seminar series in biomedical informatics. And if you have any questions, you can't find it, you lost your Zoom link, you got kicked out, please reach out to me, Liz, or Catherine. They are very knowledgeable. They know the entire content. They know how to reach the faculty, where information is stored. So we really hope you get a great experience. You learn very important and new marketable skills, and have a successful and productive career in translational and clinical research. Thank you. And I want to pass the microphone to Dr. Elkin, but please let me know if you have any questions.
Thank you very much, Katia, especially the plug for the department, our courses. That was wonderful. You're very kind, and it's very helpful to us. So I'm just going to share my screen. You seeing my screen? You guys all good?
Yep, perfect.
Okay, perfect. Thank you. My name's Peter Elkin. I'm a clinician boarded in internal medicine and in clinical informatics, and I'm also the chair of the Department of Biomedical Informatics here at the Jacobs School of Medicine and Biomedical Sciences. And we're very excited to share with you programs and research that are ongoing in our department, and also some things that we think would be of interest to the audience in terms of artificial intelligence, and then some work on quality and safety that we do that I think also will inform you. We're very proud of our Department of Biomedical Informatics here at UB. We are in the top 10% of medical schools in biomedical informatics, which means that we're contributing greatly to the overall reputation of the school and the university. We have 5 divisions in the department. The first is clinical informatics, and that deals with electronic health records and our data systems, how we work with our knowledge and provide clinical decision support back to clinicians. We have a division of bioinformatics that deals with clinical genomics and proteomics. We have a division of public health informatics, which deals with global health problems and informatics solutions. We have a division of biomedical ontology, which I think is the largest one in the world, and is leading the way in biomedical ontology development and use. And then we have a division of socio-technical and human-centered design, which does human factors engineering and ethics and things that revolve around the context of the tools that we use. And we have a large support staff. We have about 11 primary faculty, and we have about 35 overall faculty, including our adjuncts. And we have about 75 people in the department. It's a robust department. Here are some of the professors that work on projects that we have here, and most of you know some of these folks. And I saw the names of some of our people, our prior and current fellows that have been here. Some are on the call today. I'm really pleased to see you. And then we have a robust PhD program with PhD students that are absolutely amazing scientists. And we have a tremendous support staff. And there's another Prahlad Rangan who didn't give me a picture, so he's on there too. But Frank Lahullier, who's in charge of a lot of the technological work in the department. Gloria Reed, who's our point of contact and secretary. She takes care of people that come into the department. She's just wonderful. Annie Hayes Montesano, who's a lovely addition. She's our educational coordinator, and she's done fantastic work. She also does a lot with our research programs. And Winanne Conway is my assistant chair, who's absolutely wonderful. She's helping us with most of the things. And if you interact with the department, those are the people you'll see. And when you look at our faculty overall, there's quite a number of faculty. And one of the ones I'll point out that I was remiss in not putting on the other screen is Tom Furlani is now primarily with our department. And he's very important in the NSF supercomputing arena. So I wanted to point out for those of you who are physicians that we have a new subspecialty in clinical informatics. This was approved by ABMS in 2013, and there's been a board certification since 2014. I've been on the committee that writes the specialty exam, subspecialty exam with ABPM for the entire time. It's 2-year fellowship. You become expert in quality, safety, systems requirements generation, system selection, system implementation. We're starting e-consult services, and they have often gone off and become chief medical information officers or other leadership roles in health systems and hospitals and academic centers. Some of our graduates have gone into government, and some have also gone into industry. There's a long list of things you do in clinical informatics, and then they're listed here. I'm not going to read them to you, but I'll just point out that translational informatics is part of this. So getting things from the bench and implementing them at the bedside often requires informatics techniques to do properly, and people become expert in that aspect of informatics during the clinical informatics fellowship. We have a lot of educational experiences in the department. I just want to outline them in case they're relevant to anybody on the call. So we have an elective in the medical school called IMC 815. It's a clinical informatics rotation. Up to 2 students take it per month, and it's a 4-credit course, and we get really rave reviews from this. And then we have research rotations for residents and fellows that they can do. We also have a master's degree in biomedical informatics. We have the PhD, including MD PhD candidates who come through the program. And that we've had one of these so far, and the person is just outstanding. And we would love to him back at UB once he's finished all his training. We have an ACG accredited fellowship in clinical informatics. We have postdoctoral research fellowships that are NIH funded, and we have a short-term training experiences for undergraduates and master students in biomedical informatics. This requires that you are either a U.S. citizen or a permanent resident. And we have a new undergraduate major, which is getting very popular. I gave a talk to them this morning, and they were between 30 and 40 people in the lecture. It was great. And then we're becoming a thread in the medical school's education across the years. And we're planning to work with every single course director to implement informatics examples and informatics concepts into their teaching programs throughout this. We're going to put up an EMR so that all the case-based teaching can be in an EMR environment, and we will work with leaders of education in the new curriculum, Lisa Jane Jacobson and Jennifer Mecca, along with our partners that are course directors, to try to really provide a 21st century experience for our medical school students. We have the NLM T15 award. We were renewed a year and a half ago, and they increased our slots for most everybody else in the country got cut. This is the most prestigious grant that NLM gives, and we're happy to be counted in the group. There are only 18 institutions in the country that have these. We've gotten a number of supplements, and there's another one coming out that we'll get. We're excited. We have 4 postdoctoral and 4 predoctoral slots in this program. We also have a R25 that we won this about a year ago. We had our first cadre of students this past summer, and these are basically undergraduates or master's students who would like a more intensive experience doing research, and there's $5,000 in compensation for the summer for this. And if you're really from out of town, you get $3,000 for a housing allowance, up to the money that we have. And then you get 10 weeks of training. And there's a preference for underrepresented and research people to do it, but please do think about applying. You have to be a U.S. citizen or permanent resident, as I said, and you, in addition to doing your own research, you participate in the UB Summer Boot Camp. and we'll talk about that because that boot camp is now part of this program, and we'll go into that in a bit of detail in a bit. We have the master's degree, and you'll have my slides, so you don't have to, memorize these or go through them in detail here, but we're happy to answer any questions that anybody might have. So one of the things that I found it useful to talk to everybody about is what are the top 10 accomplishments in biomedical informatics that we've done for you already? These are things that we've done, and you may not know that they're associated with our specialty. So first, we created personalized medicine, precision medicine. So if it wasn't for the work between informaticians and pharmacists, the link between the microsomal enzyme oxidase cytochromes and metabolism of our drugs that we use every day wouldn't be linked to codes and wouldn't be linked to the EMR and couldn't be given as decision support to help us better prescribe drugs for taking into account people's constitutive genetics. And I think that's, and obviously, if you're not familiar with these, this is like a Letterman list going from the 10th to the 1st, which is the most important thing that we've done for you. E-prescribing. So you guys have probably heard doctors have lousy handwriting. It's absolutely true. There's no question about it. And there were a lot of med errors that came from doctors' handwriting. And we worked with NCPDP to create NCPDP script, which is the format in which all drug information and prescribing information is sent to pharmacies. And now almost all prescriptions are done electronically, and we don't have any bad handwriting mistakes that go on. And they also can be checked electronically for drug-drug interactions and drug-herb interactions and other things that people may be exposed to. And this has helped make drug prescribing safer. They also in these checks include checks for renal insufficiency and changes in dosing of medications or medications in the case of that, and also hepatic impairment. Evidence-based medicine. So if it wasn't for MESH and the coding of the medical literature, there would be no way to combine the articles in the literature meaningfully and create systematic reviews and meta-analyses that we use as the basis for our guidelines. And those guidelines allow us to have implementations that provide for the practice of evidence-based medicine. And this has all come out of informatics work. Clinical decision support. No, it's not very good right now, but it's getting better and the promise is outstanding. I want you to think about it this way. Have you ever gone bowling and you can put up those guardrails on the side that don't let you hit a gutter ball? Well, that's what we're going to be doing with clinical decision support and AI to begin with. We're going to make it so that doctors don't throw any gutter balls when they're treating their patients. And I think most people can relate to that one. Electronic health record systems. Everything that you see in your electronic health record systems came out of the laboratory. And I'm here to tell you they're not great. There's, the cream of the crap out there, but I'm just telling you they're not very great right now. But I know what's in the lab, and I'm optimistic that all the electronic health record systems are going to get better over the next 5 years. Translational research. So I'll tell you a story. You guys are here because of translational research. It was started by informaticians. So in the year 2000, a friend of mine, Andy Ballas, he wrote a book chapter that said it took 17 years to go from bench to bedside. In 2001, they published an article on the same topic. This incensed Congress. They said, we're spending all this money on research. Why should it take so long for us to go from bench to bedside? And in 2005, they started the largest grant program the NIH ever had, called the Clinical and Translational Science Awards. And now 60 of the best medical schools in the country have these awards, including UB. And this has moved it forward considerably. By 2009, the National Center for Advancing Translational Sciences was formed. And so we have made significant progress in this regard. So you might ask, okay, in 2001, it took 17 years to go from bench to bedside. How long does it take today? The answer is 14 years. And I can tell you, President Tripathi has charged me and Tim and Katia and others to cut this in half. So our goal is to get to 8.5 years. So we're not there yet, but we're working hard toward it, and we have great ideas on how to move it forward. And I just wanted to highlight the good work of all my colleagues in the CTSA are doing in order to make that happen. Mapping the human genome. 2003, Bill Clinton gets up and he says, we have mapped the human genome. What had he actually done? He mapped one person's genome. That person was an African-American person from Buffalo. That's whose genome was mapped. Craig Ventnor, whose company did the final mapping, he was a professor at UB who did not get tenure and ended up leaving. But he, in any case, his career was perfect, no matter, even though he left. But it was one person's. And now we have more than one person's genome mapped, but we certainly don't have everybody. We certainly don't have the breadth of the human species mapped. So there's quite a bit more to do. And you wouldn't have been able to accomplish that mapping, by the way, without the bioinformatics tools to find, synergies between fragments of DNA and to complete the DNA in sequence from the restriction enzyme broken up pieces of DNA that were actually sequenced in the sequencer. And that kind of homology identification was critical to the speed at which we were able to identify how to put back together the human genome. So systems that facilitate paying for physicians for high quality care, equality, happened to be my work, and this led to the Affordable Care Act, because we, for the first time, showed that we can actually identify the quality of care that a physician provides their patients. And once they knew that, it started pay for performance, and a lot of positive things happened. For one thing, it used to be that people who were bad doctors got paid more than good doctors. So a good doctor would do the right thing the first time, the patient would get better. Bad doctor would hurt the patient, and they would get paid again to fix it. And now we have incentives in place to reward people by their risk-adjusted quality scores, so that we pay people more appropriately for the type of patients that they're seeing and the outcomes that they get with those populations. PubMed. So the National Library of Medicine created a PubMed and indexed Medline, which is where the literature has with mesh codes. And this cataloging of the literature was opened in 1997. Al Gore didn't invent the internet, although he said he did. But he did do this. He made PubMed free for everybody. Before then, you had to pay for it. And this actually made access to the medical literature much better and helped to promote the use of evidence-based medicine. In addition to that, editors of journals all over the world pushed for structured abstracts, because they knew that even though the publishers would require that the articles were behind paywalls, that the National Library of Medicine could demand that the abstracts were open. And that has happened, and many articles are available that people can read quickly and use the information in their practices and in their research. But the number one thing that we're doing for you personally is taking medicine from a cottage industry where people practice the way they were trained, and to get them to practice a systematized practice of medicine. This means working in teams and working together and being responsible for patient outcomes, and not just for what you do with the patient. And this is it's a brave new world. And we need to move staunchly and with great pride into the 21st century. So I'd like to tell you about some of the research that's going on. The ones I published in the Annal of Internal Medicine, we did this project for the Centers for Disease Control, where we were predicting the presence of the flu epidemic. It took the CDC about 45 days to predict the flu epidemic. Hopkins got it down to 41 days. They were very proud. We got it down to 5 days. I got a nice letter from Hillary Clinton at the time, who was our senator, saying that she liked our work a lot. And that was great. My kids were very impressed, I want you to know. We did this other project, which was published in JAMA, which looked at the National Surgical Quality Improvement Program, which is a program that's been shown to improve the quality of surgical care in the country. And it's done by nurse abstractors in general, but that has been somewhat insufficient in that they can only afford to index for every surgeon about 10 charts a year. And that's more than they can review for everybody. And we were able to, of course, do all of the surgeons' records, and we did it as well as a very highly trained group of nurse abstractors with all of the major complications that NSQIP follows. And that was published in JAMA. We did a study we published recently on biosurveillance of non-valvular AFib, and this was a study of 63 million patients in the country. And what we found was if you had a stroke, the cost difference adjusting for inflation was about 102,000 extra in the year after a stroke than the year before. And that's where we got our cost basis. And what we found was that if we installed our system for biosurveillance, that we would treat probably another almost 4 million people in the country, save 176,000 strokes and over 10,000 lives. And the savings for the program would be about 18 billion if you subtract the implementation costs and the cost of complications of the therapy. It comes down to about 13.5 billion to the good. And this is just one disease that we'd be looking at algorithmically. We discovered the only treatment for COVID that saves lives. And this is a treatment for people who have severe cases of COVID. And we found that if you add leukotriene inhibitors to dexamethasone, that it prevents death in COVID-19 patients. There was a 13.5% inpatient mortality advantage overall. And if you were taking the leukotriene inhibitors ahead of time, it was a 22.25% survival advantage. That is better than any of the expensive drugs that have come out. And it makes sense because leukotriene inhibitors inhibit IL-8 and IL-6, which are bad prognostic indicators in ARDS, which is the primary reason why people do very poorly from a respiratory standpoint, other than pulmonary emboli in COVID-19. Well, we weren't satisfied with that, and all of our group of researchers in my research group, we did not like cancer. Does anybody on the call like cancer? No, right? Not true. So we took people who had stage 1 non-small cell lung cancer, and we found that the people with metformin had an 18% 5-year survival advantage. Well, that's pretty good. And we started to think about why that might be so. And we took it to the bench. And here's what we found. We took cell lines of both adenocarcinoma and squamous carcinoma small cell lung cancer, and we grew them in successively lower glucose concentrations. And of course, the ones with less glucose grew more slowly. And then what we did was we added back ketones to them. And what we found was that these cell lines were not able to metabolize the ketones, that it didn't rescue the growth at all. Now, when we go into a ketotic diet as human beings, our brain and heart and muscles learn to metabolize ketones, but the cancers lose that function as they de-differentiate. And so the idea is to win the race against cancer, not to kill it necessarily, but to make it grow so slowly that our host defenses can kill it. So we're trying our best to win the race against cancer. And we've got under review right now a paper defining long COVID and the risk factors for it. One of the first places we submitted, a very high impact journal, gave us a review and feedback, and they wanted us also to predict what the risk factors were for COVID. So we did that. So what we found was all the subspecialties have a separate kind of phenotype for long COVID. So there's cardiac long COVID, GI long COVID, respiratory long COVID, renal long COVID, derm long COVID, all kinds of long COVIDs. And I think what we'd like to see is from those definitions that we have, we get our colleagues in those subspecialties to look at the phenotypes, find those people who've had COVID, and try to elucidate the basic mechanisms that are at play within their specialty, because we think it's probably multi-comorbid, and there may be different pathways involved in various specialties, versions of long COVID. In terms of risk for long COVID, if you've had a more severe case of long COVID as lower oxygen tensions, then the odds ratio for you developing long COVID was 1.6. If you're unvaccinated, the odds ratio was 1.3. And if you weren't taking, if you have more comorbidities, it was 1.6. And if you were not taking leukotriene inhibitors, it was 1.5. We published a paper. There were a lot of anti-vaxxers who weren't taking the vaccine because they thought that there was a risk of venous thromboembolism. So we looked into it, and what we found was that the excess risk of thromboembolism was 1.4 per million cases of thromboembolism. If you look at the risk of thromboembolism from COVID itself, it is much, much higher. It has been up to 8% in some prior studies, 3% in others, but that's a huge risk comparatively. And the risk-benefit ratio is clearly in favor of vaccination. And we had a high-impact publication that looked at something that doesn't happen very often, which is we took clinical data from treatment registries. Well, it was actually treatment, kind of an EMR from OASIS, which are the treatment centers for addiction. And we combined it with all of their Medicaid data. And we have that in a data center here for all the people from New York State that are seen in the OASIS treatment centers that also are insured by Medicaid, which is a good share of them. We have about 170,000 people with both merged, and the method that we used was published in the Journal of Biomedical Informatics, which has an impact factor about 6.8. We have under review in Nature publications now, looking at RNA editing and the implications of RNA editing in our human disease, understanding of human disease. So when I was going to med school, they taught me that molecular biology went something like this. You had genetics, your constitutive genes, and then you had epigenetic phenomena that affected its translation. You had the transcriptome, then you translated that into proteins, and then there are post-transcriptional modifications that were responsible for the rest of our biodiversity. And if you think of that story, you mean it would be supposing that 30,000 genes get translated into 120,000 proteins, right, in the human proteome. So what we found, though, is there's another way of changing our transcription, and that's RNA editing. And this can be something that is influenced by climate change or other environmental factors, and it affects how our bodies can respond to threats that we're seeing. So what happens is these stimuli increase interferons. Those interferons stimulate ApoBac3A and G, and those cause RNA editing and DNA editing. And that pre-transcriptional modification is also part of our biodiversity and also part of what generates human disease. And we looked at registries of human genetic disease and found that overall about 5% were caused by this, but in some specialties, like nutritional disorders, it was over 70% were affected by, had the possibility of being affected by the CDU RNA editing changes that we're talking about here. So we think that this is a less well-explored area of molecular biology that deserves more attention, and we're hoping to bring attention to that. And the response to the journal, they wanted some modifications, is going in shortly. So we just published a book, Terminology Ontology and Their Implementations. That's a Nature Springer book, and we're getting rave reviews for that. The last issue was published in 2012, and that was a much smaller book. It's about 200 pages, that book, and it had 11,000 copies sold. This one is 580 pages, and we expect it to be much more popular than the older version. It's much more comprehensive, and if you're interested in learning more about the field, this is a good way to learn it. Next, I'd like to talk about artificial intelligence for health and using that in decision support. And what I'm here to talk to you about isn't using a model as a tool in your practice. What I'm here to talk to you about is changing the paradigm and thinking about human-computer partnerships, where we're going to be working with the computer as a collaborator, and an equal collaborator with us. And clearly in all collaborations, people have different skills, and it's absolutely clear to me that computers have different skills than people. But some of them, some things they do much better, and other things they don't do quite as well. And it's not any longer about just holding more data, but it's being able to analyze it faster and reason over it more quickly. And I think that in the end, we're going to continue with this idea of a human-computer partnership for the foreseeable future, rather than machines doing things alone or people doing things alone. There are lots of kinds of AI. You've heard a lot about deep learning, but I'd also like to point out explainable AI. And there are some explainable AIs, and we're going to talk about them in a little bit. But I think that, having the confidence to understand how an AI made a decision is, although not essential for people to use it, is a trust item for many in using the output of machine learning algorithms. So I'm not going to read this to you, but we all have seen things like that. All computers are perfectly designed to give the result they give. And so if you design it poorly, you're going to get a bad result. And so it's really incumbent on informaticians to do a good job, both in how they model things and also the populations they use to train the models. So the idea is to have AI for social good and not just AI for AI's sake. We're not leading the world in AI. No, China's way ahead of us in AI, and we're the poor cousin in that regard and playing catch up. But we are getting better, and we have certain talents that I think are going to differentiate us. We have access to the medical literature, which in healthcare is very empowering. I think will help us quite a lot. And you should know that although there's a core specialty of artificial intelligence that has its own methods that are used by each of these different specialty organizations, that only recently are we starting to modify these methods and make them better and more robust. The methods that were created for machine learning had not changed much from about 1991 till about 2016, 17. But in the last few years, we're starting to do better. I'm going to stick on this slide for a while because I really like it. We have these core of methods in artificial intelligence, and then we have our disciplinary core of understanding and what we're trying to do, what our outcomes are. But what we need between there and what we build as applications is a legal, ethical, and social layer that sanctions what can be done. I'll challenge you with this. AIs will become sentient. It's absolutely certain. And I believe it will take them only 20 nanoseconds to figure out that the problem with the planet are people. So we need to design our algorithms in a way that they're safe and unlikely to be of harm. And this requires thoughtful understanding of the legal, ethical, and social issues surrounding them. And then, and only then, should we build applications that use them. And this should be baked into all that we do. And when I say baked in, it could be in software, but I would prefer it was built into the hardware. And if those of you who don't know, software can be burnt into chips. So of course, we're a university, so we want to do all these cool things with AI that people haven't done before. But in this lecture, I really want to talk to you about what AI is and how this works. So we're going to start by talking about supervised learning. So supervised learning is where you know the right answer for some outcome. And you've got data on people who had the outcome and didn't have the outcome. And you train the computer to predict who's going to have the outcome based on their underlying data. And this is wonderful when you have it, and it's kind of best case. But for annotated data in medicine requires very highly paid people, doctors, to review things and to annotate them in a way that can be used by a computer. Let's say you don't have any doctors to do it, you can still use unsupervised learning. Unsupervised learning is where you don't know the relationships of anything to anything, and you don't know who had the outcome or didn't have the outcome, but you just want to understand what all of the predictors are for everything else in the data set. And this can find hidden patterns in the data, and often is used to discover new features to include in the model. Most of the time, though, what we're working with is semi-supervised learning. And semi-supervised learning is where you have a certain amount of labeled data, and then you have a large amount of unlabeled data. So you train first with the labeled data, and then in an ensemble technique, you burn in you add in the unsupervised data. And that helps to give a large number of patients' data to train a machine learning model. And then the other thing that people don't talk about as much as they should is reinforcement learning. So let's say we build an AI model, and then it's in use. These models can take feedback from the users when they get it wrong or when they get it right, and help them to adjust their weightings so that they can do better in the future. So about 2000, it was just before the pandemic, I was at the FDA giving grand rounds, and I told them that they had to think differently about approving machine learning models. And I mentioned that the real special thing about them is that they can get better over time with feedback, continue to learn. So you can't, in a normal, if you have a cat in the device area of FDA, if you have a catheter and you get it approved, you make any changes to the catheter, you have to go back and get reapproval. But here now we've got a machine learning algorithm that's going to change over time. And we told them they had to think differently. And what they ended up approving was just that. You get approved for a machine learning algorithm with a model for how you're going to continue to train it. And that plan, that training plan, gets instantiated and approved with your approval for the device. And only if you change the method of training or the underlying program in some other way, that model has to go through for reapproval. And this came out like a couple months ago, and I was so pleased that they'd listened. It's very exciting to make difference like that. By the way, when I gave that lecture, they looked at me like I had three heads when I told them they had to think differently about approving things at the FDA. We'll talk a little bit about deep learning and large language models. I'm sure they're on all your minds. These are highly accurate, but not specific enough to be an expert in any one task. They have no underlying semantics. We've often viewed them as chatbots. The concerns with education are plagiarism, and they confabulate. Concerns in research include fake data. And as you know, authors or journal editors have made the decision that LLMs cannot be authors on papers, even if you get content from asking them to write it. And we also know that it's not okay for our students to ask ChatGPT to write their term paper for them. Now there's software where you can tell if the software was or if the piece was likely written by a chatbot. They're okay. They make mistakes. People put the Bible through one of those programs and it said a chatbot had written it. So I'm not so sure they're always right. Concerns in practice are patient harm from misinformation and, of course, poor usability of some of these devices. And we're going to talk about them and what we're doing with them in the laboratory in greater detail. Let me talk about some of the base machine learning methods first. Random forest, you may have heard about, is a type of decision trees. It does tree bagging, and it tests for subsets of features, which are the trees that have a dissimilarity feature between them. So the farther away something is, the less likely it's grouped. And these are grouped in a dendrogram until they're at a level where you can deal with the number of choices. And of course, the mathematics are at the bottom for those of you who like math. And I'm not going to do math here in this lecture, but you can come work with us if you like math. You don't have to know math to work with us. Naive Bayesian classifiers are neat because they're explainable. They're completely explainable. They use Bayes' algorithm, and this uses conditional probabilities, where the prior probability is used to weight the current findings. And the way you read one of these is that this is the probability of C at K, given that you know X to be true. And the way we think of this really is the posterior probability is equal to the prior probability times the likelihood ratio, the positive likelihood ratio, over the evidence. And this is a nice way to just think about how these models work for you. Kind of a neat thing. I wanted to give you a little something on electronic health records. People don't know the history of them always. These begin in the 1960s, and the first ones were the help system in CoStar at MGH. I was a CoStar fellow when I was there. And then they started in commercial work, and Lockheed created Technicon, which was in 1963, and they installed it at El Camino Hospital and then at the NIH Clinical Center. It later became TDS. That was installed at Penn, and actually the way they installed it, it actually led to the death of 8 children. It's terrible. The way that happened was that before they did this install, if a child was picked up by an ambulance, they could call in and they would accept to get medicine ready for the child that was ready to give to the baby once it hit the door at the hospital. But after the new system was put in, it needed to be accessioned before you could order any medicines. And so that caused a 1.5-hour delay in treatment and directly led to 8 deaths. And Han, who wrote this article, actually under pressure from the EMR companies, was fired at Penn, but did find a good other job, and he's doing just fine now. But it was terrible how some of the business practices interfered with good science. Meditech, which we still use at ECMC, was written in mumps and was developed in 1969 by Neil Pappalardo, who came out of the same lab I did. Epic was started as an outpatient system in 1979 and Cerner as a lab system in the same year. Boston, at the same time, and the Beth Israel Hospital created an EMR, which then was metastasized to the Brigham and Women's Hospital, which worked for many years before they went to Epic. Reagan Street Institute had their own EMR that they built. Duke had one. The VA came along and built the distributed hospital computing program, which became Vista and CPRS, and that's still in use today, just transitioning but slowly to Cerner. In 2009, there was the ERA funding for EHR adoption, and the reason they did that was not because they thought it would improve quality of care, but it was that they wanted to know how they could reduce healthcare spending. And hospitals were saying they spend a lot of money on free care, and therefore you can't just take our for-profit payment information and make judgments about what our health would be if you cut that. And so they invested $48 billion in getting everybody implemented. And this took the country from about 38% implemented on EHRs up to about 98% with this additional funding. And now we can start to look at costs better. The hospitals still don't have unit costing, which is really necessary to do it properly, but they're moving in that direction. So we in our lab deal with the 83% of the data that's in unstructured data. This can be in documents, reports, legends of figures, tabular names, field names, and databases. And some information is just not available in structured form. Social determinants of health, although there's some coding systems that will take it, rarely is used. Signs and symptoms, physical findings, counseling, quality of life measures, behavioral data, drug use, opinions, that kind of thing are all only in unstructured data. And we created a NLP system, call it the HD NLP system, or it's a high definition NLP. And it basically is a very easy to use NLP system, which you can take unstructured data and code it in any ontology that you want and bolt it together with observational data like the OMOP database, which we have here at UB, and I'll tell you a little bit more about what's available to you in a minute. So, of course, you have to have an obligatory joke in one of these talks, and I'll let you read that one. Okay, so anyway, this work that we've done is very highly accurate. We have in 1,000, we have 3 false negatives and 2 false positives. And that's a highly accurate system. We have a program which you can get access to called the BMI Investigator. BMI Investigator is a method to look at retrospective data clinically. We have about 237,000 Kaleida patients as growing with each of the data polls. There's one being implemented now, so it's going to grow. And this allows you to search for anything you want. It you could take inclusion criteria, exclusion criteria, put them together, call it the population, save these, bring it back, ask a number of critical questions. You can recruit over one time period and then follow that population to a later time period. So there's lots of interesting things you can do with the software, and it doesn't require IRB approval. It's IRB exempt. So and you can get out of it. It comes back quickly, so you can do studies in 5 minutes. And this actually will bring you back. This query for people with anxiety came back in 18 seconds. Usually even complicated ones are less than a minute. And then immediately for the cohort that you found, you get out of it with one click: race, ethnicity, gender, and age distributions, which can be helpful immediately. Everybody kind of likes those things. And then, you can ask for whatever you need. You can download some of the data in a de-identified format, and that will help you to do any retrospective research that's appropriate to that population. And the population in there, so that is anybody who was ever tested for COVID. And so it was people who are tested, and it has their information back to the beginning of 2018 to the present. I want to tell you a little bit about ontology. The best way I explain ontology is that it provides you the computational ability to have multiple but consistent views of the same data. Not everybody comes to data with the same perspective or the same questions. And no matter what your purpose in coming to the data, it should always show a consistent picture. So here's a organ system-based view of diabetes, but just as value is a biological view of diabetes with the beta cell that makes the insulin and all of the metabolic pathways and organs that are affected by that. Here we use the basic formal ontology, which was originally developed by Barry Smith, and as the upper level ontology, and this was very, very proud to say this was accepted as an ISO standard. We use the ontology of general medical sciences for course of illness to represent course of illness. And we use underlying terminologies like SNOMED, LOINC, and RX norm underneath these to represent detailed findings. And then we personally do one other thing other people do not do, which is we build these into semantic triples or sentences, which can be built up into networks and can be used for inference. So we decided to take this and make it part of a machine learning experiment. So we took a machine learning algorithm and we trained it on what we say in medicine, which is SNOMED and all the synonyms that we have. Then we trained it on evidence-based medicine. That included the medical literature, it included clinical guidelines, it included clinical guidelines for patients, Medline Plus, it included drug databases, it included information like order sets and discharge checklists and best practice guidelines, things like that. All of the guidelines from the guideline clearinghouse, the National Guideline Clearinghouse were included. And then we did some experiments with it that we think are really telling. The first thing we wanted to know is if you build a machine learning algorithm with these pre-trained embeddings, would it improve the accuracy of the model? And we did this using the OASIS data that I told you about, that one experiment that's a merger of opioid treatment centers data and Medicaid data. And we trained the model without the pre-trained embeddings and with the pre-trained embeddings. And what we found was that it was much more accurate with the pre-trained embeddings and led to improved outcomes, but also was less biased. So as we removed data from the data set, we started with removing people, then we removed random pieces of information, then we added back bad data to the data set, and we watched how the algorithm performed and how fast it degraded. And as you can see with the bottom lines, they degraded much more quickly than the top lines, which shows to me that medical knowledge helps to decrease the bias in machine learning algorithms. And then we started to work on large language models and deep learning. These are, I talked about that slide. So I'm going to get to that. So here's what we're doing. We're trying to add a semantic infrastructure to large language models like ChatGPT and GPT-4. So imagine you have a question you're going to put to these large language models, and we use our NLP to create these networks of semantics that come through. And then we send it to the pre-trained embeddings that we've created. That is made up of 3 different layers. It has an embedding layer, it has a tension layer, and it has a feed-forward layer that will contact with the other layers in the large language model. And we're trying it a number of different ways. The first way we're trying it is with taking the English translations of the semantic triples and passing those along with the matrix of weights that were developed for not only the input question, but also all the associations that were found in the pre-trained embeddings, and pass this all to the large language model along with the original question and see if it improves the ability to answer the USMLE questions, which we've downloaded. And our hypothesis is that using a semantic layer with a large language model will improve the ability of large language models to answer accurately the USMLE questions. We are in the process at UB of getting a contract with Microsoft for GPT-4. In advance of that, we're using Llama, which is the open 70 gigabyte Meta AI open source embedding large language model. And then we're wrapping it all up in a chatbot and trying to see if we can make a digital doctor to help people who don't have access to medical care regularly, either in this country or in others. And especially in countries that are English speaking, that are foreign and third world countries, they're really looking forward to this. And then hopefully get accurate answers. Here in the department, we have lots of data sets available. I'm going to get through all this. Please do contact us if you want to be on protocols with us and collaborate on any of these data sets. We also have whole genome sequenced part of the REPOP project from the VA, which is the Research Precision Oncology Project, where there are somatic mutation data on over 1,300 patients who passed away that we can use. And this is full deep sequencing. We have a PhD program in biomedical informatics. If you're looking for a PhD program, please do consider us. And we'd like to work with the MD PhD program people as well, if they're interested in working with us. And I'm trying to think if I should go through, I'm going to go through pretty quickly because I don't have much time left and loads of slides, the healthcare value portion. So this is, we define value in healthcare as quality over cost and quality as outcome, safety, and service. And we need reliability of these functions. So Kaplan and Norton published the famous book, their balanced scorecard. And they said you can't manage what you can't measure, and you can't measure what you can't describe, which is how I got into knowledge representation in the first place. So we take people and technology and we bring them together with process. And we've gotten a lot of kudos for the research. The Government Health IT Journal said we were doing exactly what was needed. And this was part of our research was used, as I said, to start the Affordable Care Act. And so we're very proud of that. This is one of the first papers that we published on equality. So let me talk about quality for a second. This started way back in the late 1800s when we became a manufacturing economy. And, of course, after World War I, we became a service-based economy, and people have not recognized it, but I'm absolutely certain that by the turn of the century, we became a knowledge-based economy, and people have a lot of catch-up to do the right thing in this knowledge-based economy. So in addition to the Ford Motor Company, which started its assembly line, Guinness Brewery also adopted this, and that's why Guinness is very standard, no matter where you get it, as long as they sell enough of them. Guinness tastes the same wherever you have it. And those of us who love Guinness are still appreciative. The person who really made the biggest intervention in this was Schuhart, who created statistical process control, mathematics, and charts to follow what people do over time. And this has really changed the game on quality and safety. And his best student was a guy named Deming, who went to Toyota after the war and created the Toyota production system. And this really changed Toyota's quality and safety and led to the sharp uptick in sales of cars from Toyota and other manufacturers in Japan across the entire globe. And the idea with Six Sigma, of course, is we want to get our errors down to parts per million. And that's what we have, for example, in airline industry. In medicine, the error rate is about 6%. And the number of, or the percent of time where those errors lead to harm to the patient, where it touches the patient, is about 17% of those. So about 1% of the things that we do in medicine lead to harm. And that actually is pretty significant. I'm pretty sure that if all of you got onto a plane and were told that there's a 1% chance that it was going to crash, you would get off the plane. But we still go into hospitals knowing that there's a 1% chance that we'll do harm. Now, 99% of the time we do good, but on average, a resident will do 3,000 things in a month, and you can expect that 30 of them will be harm. And we've got to accept this. We've got to look at it closely, and we've got to minimize it in order to create a real culture of patient safety. And Lean came along, and Lean took a different approach. It said, look, you can get good or harm from everything you do. So let's look at what we do and see which things are actually creating value. And if they're not adding to the value, let's get rid of them because they're always a potential for harm. Lean manufacturing says that we should create value streams that make sure that everything that we are going to be doing in our business creates our value. And where it doesn't, we get rid of it immediately. So, of course, with quality improvement, everybody knows Ed Deming. He was an author and professor, and he pioneered the use of this statistical analysis that Schuhart developed to achieve better industrial quality control. He created the idea of Plan, Do, Study, Act, which is a way that we implement this in a virtuous cycle that continues to take care of the things that we need to do in order to work toward higher quality care. The way I like to think of this, though, is you've got what you're trying to accomplish, what's your aim, you've got how you're going to measure it, so you can keep track of how well you're doing, and then you have what changes can we make that will result in an improvement? What are the ideas? And then take these ideas, implement them, and then make this a virtuous cycle where we measure how we did and see if we're doing better or not, and then go on to the next idea for making things better. Patient safety, one of the ways to interpret the Hippocratic Oath is above all else do no harm. I like that one. Although my favorite is I will accept no payment before the cure. In Hippocrates' time, it was common that there was quite a lot of charlatans, and a lot of good physicians like Hippocrates used to tell people that, look, you don't have to pay me unless I can help you. And that gave people confidence that they were actually what they said they were. So we have to create safety barriers. We have to do this in our practice and do it better than we did before. I'm just going to pick on James Reason's Swiss cheese model. So hazards touch patients. They're always going to happen. People are flawed. We can't get people to be perfect, no matter how well we train them. And so what we want is, we don't want all these Swiss cheese slices to have any holes that line up. So we need enough of these in the way that the holes in our defenses will never let our problems hit our patients. So it should look more like this, that we're stopping them at every barrier, and we have enough of these successive layers that we actually are extremely unlikely for any mistake to actually get to a patient. And this is not only toward guidelines, which are minimal standards of care, but it's also toward best practice, where we embody what the best of us would do in any clinical situation. And this is very important. One of the tools that you have to use for root cause analysis when you have a bad event is what is called a fishbone diagram. And this takes categories that you have to know to understand a problem and gives you that rubric to put into your analysis of the problem. And that's, the equipment, the processes, the people, the materials, the environment, the management. It tries to get you to think not only of primary causes, but of secondary causes that may affect this, so that we can come up with plans and how we can change the systems around people to make it easier for them to do the right thing and harder for them to do the wrong thing. Another way of looking at this is a failure mode and effects analysis. And this is an example of a process diagram. And with those of you who are interested in informatics more, can go into this with us, and we will be happy to teach you the methods. This is a model of an EHR that's it's a secure model that goes through episodes of care and helps people to understand outcomes better that we created. It's built using the unified modeling language and has a way that you can actually compute over the definition of the care. This is another way to sort of represent knowledge. It's a swim lane diagram, and this is a tool that informaticians have to define who the actors are in any particular healthcare service or our workflow. And it notes the dependencies between actors. So who has to do what, and who's dependent on what, and where the bottlenecks are. This can be very helpful in analyzing patient safety events or processes that are not perfect in our healthcare institutions. We have a lot of people who create quality metrics. I work for the National Quality Forum in the common formats to help to understand better how people should be reporting patient safety events to patient safety organizations. And I've done that since its inception and development of the group. And, a lot of organizations create quality measures. This is PQRS, which is just one of them, but NCQA is measure provider. AMA provides measures as well. And we often are tasked by our payers to meet these measures, and how we get people to conform with that is an important research activity. This is just an example of coding in ICD and how people have coded in the past patient safety errors, which included people who had antiplatelet therapy, who were used secondary prevention of their coronary disease, and this included people who had a contraindication to it, as well as people who were just not treated appropriately. I think we need clinical interventions that will be clinically driven, that help us to improve our patient safety and quality, and this needs to be done with longitudinal performance measures. We implemented some in the UBMD practices that were on all scripts, and we went from, this is IHA measures, went from third to the last to first in the group by doing these measures. I'm going to show them to you now. These are the measures that we created. These are preventative benchmarks, and you can see things like colorectal cancer screening, mammogram screening, chlamydia screening, cervical cancer screening, pap smears, and flu shots, and pneumovax. There are many others. In the beginning, we gave an anonymized report to physicians, and we would tell them which letter they were, but we wouldn't, and they could see everybody else, but they wouldn't know who their colleague was that was in any particular spreadsheet. And then we also did asthma and COPD. We were doing well in those, and we could sum those up for a provider, how they did in their diabetes measures, how they did in their cardiovascular measures, how they did in their preventive measures or asthma. But we could also do it for whole practices. So this was the UBMD medicine practice over time, and this was a year rolling average of data over here. And you can see there's more measures. This is MedPeds program and how they did with the measures. So we don't expect, because it's a rolling average of a year over every month, we don't expect to see huge changes in any month, but we expect to see overall improvement. This was used to improve the practice. What we found, and we're actually publishing, is that midway through this, we decided to put the people's names on it open so everybody could see who everybody was. And all of a sudden we got real changes in the measures. And so we're publishing the fact that you have to do this. If you really want real change, you have to do it in an open and visible way, so that everybody can see them, because people are naturally competitive. Before I came to UB, I took a consulting job for Aetna, and we did all the clinical interventions for their ACO products. This is when ACOs first came out, or accountable care organizations, which is a way that places of business can contract with healthcare providers directly to give care. And as you may or may not know, private insurers often take up to 29 to 30% of the healthcare dollar. Now, Medicaid and Medicare have 10% overhead. Mostly Medicare and Medicaid believe that what's reasonable is about 15% for private payers. And the rest, they're tasked by the Affordable Care Act to have some benefit back to the practice if they're going to do it. And they should also do it under the caveat of shared savings with physicians. Initially, it was thought that that would be 50% of that gap, but which would be about 7%. But it turned out that the payers have really given us about 8% of that money, which is less. But we're, healthcare is like a grocery store. We're a 2 to 3% margin business on a good day. And if you think about 8% of 7.5, or yeah, of 7.5, that's still a reasonable margin for us and helps us to justify what we do in our practices. And this is things we want to do anyway. So we created just 6 clinical pathways: one for congestive heart failure, community-acquired pneumonia, osteoarthritis, venous thromboembolism prophylaxis, and surgical complications, diabetes. This, just those related to a savings for each of their covered, hospitals that they work with, of $67 million a year, which we thought was very helpful. The utility is it identified high-value programs and use healthcare organizations themselves to improve care and control costs, and to incent them to do it and get the shared savings from that. Nowadays, we use risk-adjusted quality measures, how they get paid, and then, of course, the payers get paid by the risk-adjusted, the risk of the covered lives that they have in their portfolio. And this is much better than before. So the idea was, we're not just trying to recommendations for safe practice, but try to move toward best practice. And that required a adoption of guidelines and of working as teams like we haven't before. So here, this was an article by Rick Hayward from Canada, who did this thing about why doctors accept the use of guidelines. And this was his reasoning. So decisions in trials lead to outcomes, which lead to data pooling, analysis, and publication. This goes through an evidence-based review process that creates a guideline. The guideline goes through a guideline implementation process that elicits clinical feedback, and that gives us reasons for new clinical trials. The number one reason why people accepted guidelines was that they were used by a trusted colleague that they admired. So in the pathways that we created, we wanted to be able to easily implement them and have not only financial outcomes, but clinical outcomes. We looked at the processes involved, the literature, and what our ability to implement them was. And we created these guidelines to clinical transformation. And this was a set of collaborations. So here's an example of the savings that this is the head screen we justified. There's a lot of CHF admissions, and CHF is the most expensive diagnosis that we have in healthcare. And a high proportion of the people, up to 27, 28%, are readmitted within 30 days. And this is a very high average cost and leads to a big cost for a hospital that has even a modicum of admissions. We looked at what the obstacles to good care were, and I have to go fast because we're losing time. And then we took the whole team and involved them in getting things better. So we took a transition management person, a outpatient treatment of diabetes. We took care coordinators and nurses. We took physicians and dietitians and smoking cessation counselors and put them together, and each had their own role in the projects. And then we had a set of responsibilities for each of the people. And I'll just say the physicians to follow the clinical guidelines, maintain fluid balance and congestive heart failure, to aim for documenting the diaries that they do each day, twice a day, and monitoring the patient twice a day, both with laboratory values and by listening to them and understanding the level of diuresis through the eyes and nose, and also from listening to the lungs. and monitor electrolytes at least on a daily basis. And then utilizing the order sets and discharge checklists and getting them to stop smoking and things. And of course, this is the ACC/AHA guideline that can fit on a card. Most of us can measure this or can memorize this and put it into use. And the idea is when you distill things down that they're simple enough, people can follow them. But it doesn't always happen. If you look at the data, only 18% of cancer care is guideline appropriate. You can say, well, there are people who are outside the guideline reference and the inclusion criteria, exclusion criteria for the guideline, and that's true, but it's not 82% of the population. It's maybe 15 or 20% at the most. And so we have to do better. So I'll leave the slides for people, but we did community-acquired pneumonia, we did VTE prophylaxis, we did osteoarthritis, we did surgical complications, and we did diabetes mellitus. I'm just going to tell you a little bit about the surgical complications because we did a lot with that. Here, this is sort of interesting. You see here, we want to focus not only on these people that are dying at a higher rate than the average, but we also want to know what the people are doing here at the back. Are they operating unnecessarily at people, or are their techniques better? Are they washing their hands better when they go into surgery? Are they getting their Foleys out quicker? You know, what is it that they're doing that are helping these people have better outcomes? And for each of the different outcomes, we can track the same kind of graphs that can help people to understand who's doing better and how we can drill down on these subsets to help people understand the phenotype of these individuals. Just going to get past some of these because there's a lot of the same stuff for different quality measures in here that you're welcome to look at your leisure. This is, for those of you who don't know, this is what an order set looks like. And this is for surgical care and what you do post-op. Here's a surgical checklist, what it looks like. Here's discharge and a post-operative discharge instructions, just to give people who are perhaps not surgeons, look at what these things look like and how they can help you. And as I'm running short on time, I'm not going to spend more time on that. We have a summer boot camp, which became part of this CTSA program. So we used to do a number of lectures, and one of the feedback from the sessions was we wanted to people who wanted more skills, you know, they wanted more skills development during the informatics portion of the CTSA workshop program. And in discussion with Dr. Noyes, we invite you all to join our free Summer Informatics Data Science Bootcamp. And this has the following lectures this year and maybe more next year. And we grow them every year. And this year we had 411 attendees from 46 different CTSA sites across the country. All of the clinical informatics fellows in the country take this as the beginning of their didactic. And all the people from the T15 programs at the NLM are invited. All the people from the CTSA consortium are invited. And NIH comes to this in large force as well. We teach technology to MIT and Caltech and to Stanford and UCSF and Harvard and Yale and Vanderbilt and Duke and probably whoever else, Pittsburgh, Michigan, whoever else you think is good in the country. They all come and they learn from UB on these topics, and it's very well attended, and the feedback is very good. About just as many people think it's too hard as too easy. So we think we've hit a sweet spot, but what we're going to do this year is drill down on the physician component of the physicians who took it and see if there's some preparatory work we need to do to get them more comfortable with the technical part, because we might be we might be getting some feedback. I got some feedback that maybe we needed to do some more remedial things for that group of individuals. And so for the next year, look for things like that as part of the armamentarium that we're going to be developing for you. If you want course credit for this, you can sign up for a course in our department. We get your course credit. You have to pay tuition then. The president and provost know about this program and are still letting us do it, even though we don't charge for the education. I'll tell you, we have gotten more good press from NIH and around the country for this program than would have been possible to buy with the same amount of dollars that we are giving away in free education. And, several years ago, MIT made all their education open source, and it has not hurt them in one bit. Stanford's doing that now. In any case, this is the educational programs that we have. I'm going to just pass through that because we've done that already. I should have apologized. That's repetitive. Oh, this is a picture of our R25 students for the last year. These are people who are undergraduates or master's students who get paid $5,000. You have to be a U.S. citizen or a permanent resident to do it. If you're in that category and you want to do it next year with us, please do apply. It's a wonderful program, and you take the boot camp, but you also do research with us, and it's a fun 10-week program. People who are from out of town can also get a $3,000 housing allowance from the grant, which is nice, I think. And everybody looks happy, don't they? The whole idea here is that eventually we'd like to turn our practice of medicine into a learning health system where we take data every day from our health system and we give back with better predictive analytics every day. We implement it using team science and implementation science. We use precision medicine to predict things that are important for outcomes in medicine, and we use these every day to make our practice better. And so as a community, we are learning every day about how to take better care of our patients, and we do it in a science-based and algorithmic way that help us to get to a situation where we are very proud of the care that we can give to all of our patients. Some of our conclusions are that clinical decision support can assist clinicians in caring for their patients, that biomedical informatics is partnering with clinicians, other clinicians toward safer and more effective clinical care, that we deal more with, more than with computers in medicine, and that there's a new clinical informatics ABS approved subspecialty, which people in medicine can go into. Please consider doing a fellowship if you're a doctor and you want to do this as a career. It's a lot of fun. Our NLP is highly accurate and has been very useful in creating a lot of the tools that we're providing you. And I'd like to close with just two quotes, and then I'm happy to take questions. The first is from Machiavelli in 1505. He said, "There's nothing more difficult to take in hand, more perilous to conduct, or more uncertain at success than to take the lead in the introduction of a new order of things, because the innovator has for enemies all those who've done well under the old conditions, and only lukewarm defenders and those who may do well under the new." And this is so, even though it was written in 1505, it's so applicable today. So my favorite quote is from Peter Drucker, who said, "The best way to predict the future is to create it. Come create the future with us. We're excited to have you." This is Mont Saint-Michel, if you don't know it, and it is a monastery on a mountain, and it took 1,000 years to build. And the third and fourth generation that worked on it knew for sure that they wouldn't see it fully completed, but they worked on it anyway. And they're part of something bigger than their own existence. And so my plea to you is, don't just go for low-hanging fruit in your research, but take on projects that are big, hairy, audacious goals. Even if you don't solve the whole thing, you'll make a dent in it and people will build on your work. You take on problems that are worthy of your intellect and make a difference, change the world. And I thank you for your kind attention. And with that, I'll stop sharing and take any questions that anybody has.
Hi, Dr. Elkin. We have a question in the chat. It reads, in the free course, how much is geared towards drug discovery?
There's a fair amount on that. There's it depends on how you take it. In a technical sense, you could use all of it as drug discovery, but there's about, I think, 5 or 6 courses on drug discovery or lectures on drug discovery in there. And there's some that are directly about that, that are definitely about it. On the slide, I think the link to the URL for the schedule's on there so that you can look at it and see what you want, whether it looks right to you. Maybe I can, hang on, I'm still put the schedule URL in the chat for anybody who wants to get at it. Are there any, it's been virtual to date, so you don't have to show up in person. You can be anywhere in the world and do it. And it would be impractical otherwise. You get into our Jupyter Hub and can use the Jupyter notebooks, which are skills building, and you can write code and see the analysis of the data and get answers right away. So it's actually empowering, and would be fun, I think, for anybody who's got an interest in this area. And if you get the bug and want to do it as a career, please get in touch with me. We would like to encourage your interest.
We have another question. Is the summer boot camp only for students, or can professionals apply too?
Yeah, anybody can do it.
Can you tell a little bit more about how to access the actual recordings for everybody?
Yeah, once you sign up for the boot camp, they're on UB Box, and you'll get access to the Box account. So you have to be UB, even if you're an industry person. No, you don't actually have to be UB, but there are some universities, I'll tell you, the only problem we've had, some universities block Box accounts. And so give us your private email if that happens, and then we just give access to the Box to your private email. Then you should be able to get access to the recordings.
Can you post the link to the registration for that?
The sign up. Yeah, hang on. We see free is good, right? We haven't had that many people who took it for credit, but I have been asked that by especially current students. Well, I certainly want to encourage questions. And if you think of something later, I'll put my email in the chat. You can write me. We are excited to be able to lecture to you. We are thrilled that you're here, and we are very interested in encouraging your interest in biomedical informatics, whether it be small or large, and let us help you to get to where you need to go to have the career you want. Meanwhile, it's nice to see some of my colleagues that joined. It's wonderful to see you on the call, and also some of my old trainees that are here. And I thank you for coming. It's very exciting, and I look forward to hearing from some of you who might be interested in this area of inquiry.
Thank you. Thank you for giving this talk today, and thank you everybody else for attending. Again, please fill out the survey. We appreciate your feedback. And if you don't get a chance, I'll send an email in the morning in case you missed it. So thank you all for attending. Have a great night, everyone.
Bye-bye, everybody.